minus accepted. So this is what is really going to be the CDF of, say, fx x square fy of x, where y is in x square actually. And hence you can also find what you call the PDF of it. That is going to be fy of x, okay, and what? If you differentiate it, you're going to get, say, f small fx evaluated at square root of x times 1 over 2 square root of x minus fx evaluated at minus square root of x times minus 1 over 2 square root of x. Okay, so this is what you're going to get, and hence small f. And hence you can simplify it to be 1 over 2 square root of x times fx of square root of x plus fx of square root of minus x. Okay. Now here's an interesting question. How about if I take now y to be, some complicated function, x cubed plus x square minus 1, something like that. Now this trick would not work. This trick would not work. And you can't find the CDF of this y directly from what you call the CDF of x. This would not work. So can we know that in what situation this trick would work and in what situation this trick would not work? The answer is yes, you can know it. And let's put this answer in the form of a theorem. Let's put this result in the form of theorem, that in what situation you can apply this trick. Okay. All right. So here's the theorem that says that suppose x is a random variable with density fx, and g of x is an strictly monotonic function, okay? Is strictly monotonic. In other words, it is either strictly increasing or decreasing. Okay? What is the meaning of, say, strict increasing? That if x is bigger than y, then g of x is bigger than, if x is bigger than or equal to y, if x is bigger than y, then g of x is bigger than g of y. Okay? That's a strict increasing. So you can have a strict decreasing actually. If x is bigger than y, then g of x is less than g of y. So that would be strict decreasing. So I hope that you remember these definitions. And once you have an strictly differentiable, a strictly monotonic and differentiable function. So this is differentiable function. So it's monotonic and differentiable, and hence continuous as well, because if something is differentiable, it is also continuous. Okay. Then the PDF of y equal to g of x can be given as what? So it can be given as this. So fy of y is equal to fx evaluated at g inverse of x, okay, times the absolute of the derivative of, so fy of y, so I need to put a y here, derivative of g inverse of y with respect to dy. Okay? This is the case if y is equal to g of x for some x and equal to 0 if y is not equal to x, g of x for all x actually. In other words, so what does this result is telling you? So it's telling you, imagine you know the random variable, in its PDF, and you have a function that is strictly monotonic, because a strict monotonicity would give you the invertibility, that the function is invertible. Okay? In other words, g is invertible or strictly monotonic and differentiable, and you can differentiate it because you need differentiation here. Okay? Then the PDF of y equal to g of x can be given as this formula. Okay? It looks a complicated formula, but you will see that it's not that complicated. Formula is straightforward, and there is almost a one-liner proof of this theorem. So what is the proof of this theorem? So the proof of this theorem goes like this. So let's compute, say, fy of y. And this is equal to probability of y less than or equal to y. But y is g of x less than or equal to y. Okay? So imagine g is increasing, then should be also invertible. So I can write this as x less than or equal to g inverse of y. So if this is the case, this is same as fx at g inverse of y actually. Okay? That's y of y. So if you want to find the PDF, you need to differentiate actually. So if you differentiate, you're going to get fy of y, and fx will become small fx evaluated at g inverse of y times the derivative of g inverse of y with respect to y. Okay. With respect to y. So this is what is really going to be the formula. Okay, I'm leaving this fact for you to figure it out, that why you have an absolute here actually. So roughly this is what the proof of it is. And then you can apply it to find, say, the PDF of any kind of random variable actually. Okay? So say you have, say, y. So you have x, whose PDF is, say, fx, and you want to find the PDF of x power n using this formula. Okay? So in other words, your g of x is really x power n. And what would be the inverse of this? So I can find the inverse by saying that, okay, give this name y. So the x is really, what do you call, y power 1 over n, that is, the g inverse of y is y power 1 over n. And what would be the derivative of g inverse of y with respect to y? So it's going to be 1 over n and y power 1 over n minus 1. So this is what it is going to be. And now substitute these values into this formula. Okay? So the fy of x is going to be fx, and substitute the g inverse of y, but the g inverse of y is y power 1 over n in this formula times the absolute of what? Absolute of this derivative, which is 1 over n and y power 1 over n minus 1. So this is what is really the CDF of what do you call y equal to x power n. Okay, so you can take any invertible function or monotonic function which is increasing or decreasing, and you can find the CDF of that function actually. So y equal to g of x, where x is the random variable, when g is a monotonic function. So this is what the trick is. So either you can apply the trick or you can directly apply this formula, okay, to find the PDF. Okay, but you have to assume, you have to be careful that your G should satisfy these assumptions actually. Okay.